So let's continue our discussion of the Schwarzschild metric. We found last time that in terms of the Schwarzschild coordinates, uh, the space around a black hole was divided into two sectors. Okay, there was the region below the Schwarzschild radius and the region above the Schwarzschild radius. Okay, and from the perspective of an observer very far away, okay, remember a Schwarzschild coordinate system is simple only for an observer which is very far away, because only for a far away observer the space-time become Minkowski, and then which is flat, in which we understand time and space coordinates in an intuitive fashion. Now we can parameterize space-time in any way we want. Some of those parameterizations will be intuitive, some will be rather complicated, and we just began our discussion in a natural way using what appear to be ordinary polar coordinates for the Schwarzschild metric. But of course, as we mentioned, the Schwarzschild metric tells us how space-time behaves, and so our original a decision on what coordinates to use becomes a matter of the solution, not a matter of the statement of the problem. Okay, and so we get some surprises. For example, we had a surprise here that if we dropped a a light ray into, or directed it toward the origin. So here's my fist is the black hole, and I direct a light ray toward it. Then from the perspective of an observer very far away, the light ray approaches the Schwarzschild radius, and as it does so, there's a redshift, okay, which becomes as large as you like as the particle gets closer and closer to the Schwarzschild radius. Why is that? Remember the statement of the solution, the Schwarzschild radius, the G00, the coefficient of the time squared in the metric goes to 0 as you approach the Schwarzschild radius. We learned from our discussion of the redshift that means that there's an infinite redshift as we go in. Okay, so in other words, as the light comes in, or let's say as a spaceship approaches the Schwarzschild radius and signals a distant observer, okay, the frequency gets redshifted as much as you like, okay, and so the time between the pulses becomes as large as you like, and okay, and the communication becomes stuck, okay. Okay, and so that's the problem. And then the challenge is, well, is that a general notion of the geometry, or is that a property of the coordinate system I'm using? I'm trying to follow the track of a particle in toward the black hole from the perspective of an observer very, very far away. Okay, that's not the way I like to do experiments. I like to do experiments with a local observer. Okay, and that's what I see, and I'm going to try to understand that. I saw, we plotted out the future light cones, both outside the Schwarzschild radius and inside the Schwarzschild radius, and we came up with the conclusion that inside the Schwarzschild radius, no particle could get out, because there's a logarithmic barrier here. And all of the light cones, the future light cones, bend over toward r equals 0. So everything ends up heading toward the singularity, eventually to be destroyed in a region of infinite curvature. Okay. Okay. So now we come to the problem. What in this description is special to this coordinate system? Okay. This coordinate system is simple, only for r very much larger than Schwarzschild radius. We want to know what is truly geometrical. So let's face that problem by doing a Gedanken experiment. Let me take an infalling spacecraft, and I want to understand space-time from the perspective of the captain. Okay, so you're the unfortunate captain of a spacecraft. You don't have any propellant left, and I'm dropping you into toward the mass. Okay, so you're falling along a radius, and you can do experiments. Okay? In particular, you carry a clock. You can make time experiments, for example. Okay, so we want to understand the trajectory of the spaceship. We want to understand what measurements the captain can make in according to his clock, the proper time carried by the spaceship. Okay, so the spaceship, of course, follows a geodesic, and here I've written down the geodesic for the spaceship, and I've written it down in terms of a covariant velocity rather than the contravariant velocity that we're more used to. I write this down for good reason. We'll see, because if I write down this geodesic for the covariant velocity of the spaceship, I'm going to find some conservation laws that are going to help me solve for the actual trajectory. Okay, so so that's the scheme of things. So u, the variable u, as usual, is the velocity of the spaceship, and if I write down the geodesic in terms of that variable, then here it is, and the minus sign coming from the fact that I'm looking at the geodesic of a covariant vector, not a contravariant vector. Okay, that's something we studied long ago, and so I want to clean up this formula and find out how the velocity of the spaceship changes as a function of its proper time, tau. Right? That's how we had a path labeled by a proper time. I found this geodesic, and this writes it down. Okay, so here's the non-trivial term in the geodesic, and I'm writing it out here. I know what my Christoffel symbols are in terms of my metric. I write that out. Okay, I have the sum over mu and the sum over rho to take. Right, sum over rho, sum over the repeated indices. I have 4 equations here, sigma going from 0 to 3. Okay, and so I put in my Christoffel symbol. I raise the indices appropriately with my upper G, right? I see what that does. For example, the G sigma alpha. Okay, but then G rho alpha raises this rho to an alpha, and so here I have a contraction of this stuff with indices, with this stuff with indices. Okay, it's symmetric in alpha and mu, and so only the symmetric piece of this contributes, and I do that arithmetic, and I see it's just one term, which I've written down here. So I see my equation becomes rather simple. Okay, it says that the rate of change of the covariant velocity with respect to the proper time of the captain is proportional to the derivative with respect to that index of the metric, then contracted into the velocity like that. Okay, so I see a conservation law. Okay, because in certain I know my metric, my Schwarzschild metric has no time dependence and it has no phi dependence. Okay, it's spherically symmetric and it's time independent, it's static. And so this character is equal to 0. Oh, okay, for the case of sigma equals 0, and the case sigma equals phi. Okay, and that's written down here. So that means I have some conservation laws. Okay, in the case of sigma equals 0, I'll call that the energy. That's okay because the right-hand side is 0, so I get a conservation law, and the 0 component of the covariant velocity is, I'm calling it energy, it's conserved. Okay, and now similarly the phi component of the covariant velocity is conserved. I'll call that minus the angular momentum, L. Why the minus? Well, the minus is because this is covariant, not contravariant. Okay, and that minus sign will clean up some of my notation later along. But you see, if I was in Minkowski space, then this would be sensible. Okay, because this is a lower index, and the upper index would differ by a plus sign, and it's the upper one, which is my conventional coordinate. What about the theta direction? Okay, I can look at this for the theta direction. This derivative is not generally equal to 0, but if I look at it, okay, I look back and I see that the the metric in the phi direction is minus r squared sine squared of theta, just that bit of the polar coordinate. Okay, that's the only contribution that I get to this equation. Okay, I'm choosing sigma equals in the theta direction. Okay, okay, and then I have so I'll get a non-zero contribution only for those g's which have theta in them. Okay, that's the g with phi. That's the only theta dependence in my metric. Okay, so I have to take this. This particular contraction. Okay, and this character is this equation reads like this. Okay, is equal to 0. This term is not generally equal to 0, but I see when I take my derivative, it goes like sine theta cosine theta, which vanishes at theta equals pi over 2, down to the equator. Okay, and so if I choose theta equal to 0, then I see that u sub theta doesn't change, and I stay there. Okay, so I see that orbits in the Schwarzschild metric are in fact planar. Okay, I just have to label them properly. Okay, this is generally true, of course. The theta plane is no different from any other plane in a spherically symmetric environment. It's just that with this particular coordination, I see clearly that if theta is equal to pi over 2, that I stay in that plane, and so that's generally true for any plane. But anyway, so I'm thinking about then theta equals pi over 2 when I come to set up my problem. Okay, so the Schwarzschild orbits are planar. That's good. I'm going to use that when I continue along my way. Okay, and so now I know a little bit about the motion. I know these two characters are conserved. I know that motion is planar, and so I can get my contravariant vector as well. So I raise my index from u0 to u upper 0, and that brings in g0, 0. Okay, and I read that off the metric. Okay, so this is the first time we've really seen examples of doing some physics with a non-trivial metric. Okay, see how careful I have to be about raising and lower indices? I have to really be careful about contravariant versus covariant indices. So it's an example of doing the geometry in one coordination or another. We saw in differential geometry how important that was, and here's an example in the Riemannian case. Okay, then I have my my r component of the velocity. I'm just writing it out in definition. My theta component is 0. It remains 0. My phi component, okay, my metric is always diagonal, so it's very easy to raise and lower indices. And I pick up a factor of 1 upon r squared with a minus sign, so the right hand side becomes 1 over r squared L. You see that I swallow up a minus sign. That's why I use the minus L over here, so that this one, well, my contravariant variable will be simple. That's what I want. Okay, so how does the spaceship move? Well, the spaceship moves according to the laws of relativity. U dot u, that the length of the 4 vector is equal to c squared, and I've written that down. Okay, that's a scalar. If I'm unsure of what its value is, well, I just jump to a locally inertial frame where my spaceship is at rest, and then u dot u is clearly c squared. Okay, and I use that frame to calculate it, but it's a scalar invariant, so it's true in any frame, and so I'm off and running. So now I can just write down u dot u equals c squared in my Schwarzschild frame. Okay, and so I just collect my terms, my 0, 0 term, my r term, and my phi term like that. Okay, and now I can write this down. I'm interested in the rate of change of the polar quote distance from the origin with respect to the proper time of my captain. I isolate that term, and I get all the other terms over here. Okay. So this is an equation. We're going to study it considerably later. What I want to look, and it's completely general, you see, and it's just a simple differential equation. It's very similar to equations that we've seen in Newtonian mechanics, and we'll make that analogy later. But I'm interested in taking my spacecraft and letting it fall into the black hole. So I'm taking the case of L is equal to 0, no angular momentum. And let's just say it starts at rest at a certain distance. So here's my black hole. I'm at a Schwarzschild coordinate capital R, and I let it go. It's attracted to the black hole, and down it goes. Okay, it starts at rest. If it starts at rest, then at the point little r equals capital R, this term is absent. I can solve for E squared, and it's given by this formula. Okay, I'm outside my Schwarzschild radius. Okay, and so the right hand side is indeed positive, all is well. Okay, okay, okay. Okay, and so I put that into this equation. L squared term is gone, and E squared is equal to this. I put that in, and my equation of motion becomes that. Okay, so now I can answer my question. Okay, I want to know how long, according to the captain's wristwatch, does it take to get a certain distance. So in particular, let's start off at a given capital R, and let him go all the way to the origin. That's a very bad trip for him, okay, because he ends up at the singularity, ripped apart by tidal forces. Okay, but anyway, it's something I can do, because here I simply solve for dr by d tau. Okay, okay, and I flip this. This term gets flipped over, and I get the integral. I can integrate d tau, okay, as a function of r. Okay, so I'm just solving for d tau. So I throw this onto the other side of the equation. I take the square root, okay, I flip it over. I get d tau is equal to stuff times dr, and I integrate. So I get tau, the time it takes to get for the spaceship to get from capital R to the origin is this. Well, that's a conventional integral. I can look it up using my tables, and here's the answer. Okay, nothing particularly peculiar about it. Okay, I learned two things. It takes a finite proper time to reach the origin. Okay, okay, and the Schwarzschild radius played no special role in the operation of the captain's clock. So now I know. Okay, that I had a coordinate singularity and not a physical singularity when I solved for the Schwarzschild metric in those Schwarzschild variables. Well, another way to check that, of course, is perhaps to calculate some of the components of the Riemann curvature tensor and see that they have no special behavior at the Schwarzschild radius. Okay, okay. My metric is sensitive to how I coordinatize the problem, but of course my tensors, my curvature tensor is not. It's just a geometric object, and so it tells me more about the reality. Another thing tells me about the reality. Reality is the proper time on the clock of the captain. Okay, that's a local measurement. He looks at his clock. Okay, he goes through the Schwarzschild radius and registers a certain amount of time. It's not a very large time. You can evaluate it for certain cases, and I recommend you do that. It's done in the homeworks. Okay, and see that he passes through the Schwarzschild radius, and nothing dramatic happens. Okay, okay. So I said RS I conclude is a coordinate singularity. Okay, and it's a coordinate singularity because because it's really the Schwarzschild coordinates are relevant for a distant observer, not a nearby observer, and so I get so that faraway observer sees things in a way it's truthful. They're the correct answers, but he doesn't get a good view of everything. Okay, because the Schwarzschild radius is a surface of infinite redshift, to him it says it takes an infinite amount of time, okay, for the captain in his falling spaceship to pass through the Schwarzschild radius. He never sees him pass through, in fact. Okay, but in fact the captain does. It's just the coordinations are not related in a local fashion, and if you're actually doing experiments, near the Schwarzschild radius, don't use the coordinates of the that we started with. Use other coordinates. Okay. Okay. Well, we've learned that no matter how, in fact, we can show that no matter how we parameterize space-time, R equals 0 is a geometric singularity, and R equals Rs is an event horizon, a surface of, and also a surface of infinite redshift, and we'll be discussing that and making that compelling as we go. We saw in the case of the plots of the light cones in Schwarzschild variables that if you start a particle out inside the Schwarzschild radius, his future lies at R equals 0 because the light cones are tilted. Okay, and that will be truthful as a matter of the geometry of space-time outside the singularity. The Schwarzschild coordinates have this logarithmic singularity at the Schwarzschild radius because you're asking a non-local question about the measurements, right? You're asking for example, for the time it takes a particle to fall into the Schwarzschild radius from the perspective of an observer very, very far away. So light has to travel from the surface of the Schwarzschild radius all the way out to that distant observer, and we found out that because of the infinite redshift, it takes forever for that to happen. Now, in the supplementary lectures, I'll take a look at other coordinate systems where the fact that the particle can easily penetrate the Schwarzschild radius and then get sucked into the singularity is apparent, right? We know that has to be the case because we just solved that. We just imagined a particle falling into the black hole. We saw it took only a finite proper time for that to happen. So that's physics. That's actually happened. That's based on local measurements. Okay, so that's the reality. And then we want to come up with coordinate systems, okay, in which we can parameterize that reality in simple ways. The Schwarzschild coordinates don't satisfy us for that. So we go on to others, and then you'll see, if you're following along with the supplementary lecture 11, I transform from a Schwarzschild metric to what's called Eddington-Finkelstein variables, okay, in which that coordinate singularity is removed, okay, and then I see in those variables, okay, the particle that's dropped into the black hole just rambles right through the Schwarzschild radius without any problem. Okay, but once he's inside the Schwarzschild radius, okay, the light cones are tilted over toward R equals 0. They tilt in a continuous way rather than abruptly as in the Schwarzschild parameterization. And so the black hole, so nothing can escape from the black hole once that object is inside the Schwarzschild radius. That's clear in Eddington-Finkelstein coordinates, and then there are even more sophisticated coordinates called Kruskal coordinates. Okay, and they're discussed in the supplementary lecture 11 and in chapter 12 of the textbook, and they're studied much more thoroughly in more sophisticated books. Okay, it's good enough for us to do it at this level. So take a look at the Eddington-Finkelstein variables. A very clever and simple transformation on the Schwarzschild coordinates, and then you'll get a coordination which reflects better what the captain actually sees, that he can fall into pass through the event horizon, okay, into the inner region of the black hole, and also never escape. And you can see the pictures of the future light cones for particles inside the Schwarzschild radius as well as outside the Schwarzschild radius. Okay. So next we'll take a look more at the particle dynamics around the spherical mass, and learn a little bit more about the dynamics of curved space-time. So we'll pick it up there next.